Okay, this is a video for discussion section, and today we want to talk about a chain rule, second derivative, Hessian matrix, or something like Looker maximum and minimum theorem. Okay, let's go. First, we want to talk about a chain rule. In our setting, this z is equal to f of x comma y. And x and y are the functions of t. Okay, in that case, we can differentiate the z with respect to a variable t. Then this is the formula for a chain rule. Let's think about it. Our z was a function of x and y. It is a function of x and y. And you know that x is the function of t. X is a function of a variable t. And y is also a function of variable t, right? So in the last line, there is only a variable t, right? So we can think that z is a function of t, okay? So since there is only variable t, we can differentiate the function z with respect to t. It is not a partial derivative because there is only one variable t, okay? So we use d notation here. So to obtain dz dt, you need to focus on z and t and find the root joining z and t. There is one root and the other root is like this. Let's see that z is a function of two variables. So we can think about the partial derivative, right? So for the first red line, we can say that z can be differentiated by a variable x, okay? Here, we can say that z is differentiated by dy, and x is a function of a variable t, and it is a single variable. There is only one variable t, so we use d notation, okay? This round notation is for a partial derivative, but this d is not a just a normal derivative, just a user derivative. Okay. Here also, then we can say that dy dt. Okay. Then you can see that here to find dz dt, we found two ways joining z and t, okay? For the first root here, first lines here, we get dz dx and dx dt. We just multiply these things. So we get here, let me see, dz dx, this one is same as df dx because z is just df in our setting, okay? Dz dx and multiply by this dx dt, dx dt. This is the first line, first path, okay? And then we add another path. Here, dz dy is the same thing with df dy and multiply by dy dt here, dy dt, okay? So you can memorize the formula like this using this tree notation, tree diagram. Okay, dz dt is dz dx times dx dt plus dz dy times dy dt. Okay, the important thing is applying to the problem. So let's think about the problem one here. Since z is a function of x and y, we can say that z is a function of x and y. And you know that there is x is a function of t, so x is a function of t, and y is also a function of t. It is given by this cosine t, okay? Then in the case, yes, we want to find dz dt here. So let's think about z and t here. There are two ways joining z and t, okay? There are two ways joining z and t. So this one and red one. Okay, cool. So for the first one, you can see that it is dz dx. This line represents dx dt. And this line is for dz dy. And this line is for dy dt. So dz dt is given by dz dx times dx dt. This is the path for blue one, and we add the red one. So dz dy times dy dt. Okay, cool. So to calculate it, we want to calculate dz dx here. Since we know the relation here, we take a partial derivative with respect to x. Then we get 2xy plus 3y to the 4 times dx dt. We just take a derivative here, then we get 2 times cosine 2t, okay? Plus dz dy is x squared plus 12 times xy cubed. And times dy dt is minus sine t. Okay? Okay. If you want to explain dz dt, if we want to write down dz dt as a function of t, then you need to put x and y as a given equation like this. X is a sine to t and y is a cosine t. Then we get 2 sine to t times cosine t plus 3 cosine to the 30 times 2 cosine 2t. Okay, plus x squared plus 12 times x times y cubed times negative sine t. Okay, this is dz dt. Okay, this is dz dt. And you can see that we want to find dz dt when t equal to 0. So if we calculate it at t equal to 0, you know, sine t is 0, so it must be 0. So this term, we don't need this term. Here also sine t here. Oh, this term, we don't need all terms. So we get 6 times cosine 0 is 1, right? So 6 times 1, it is just 6 times 1. 3 times 1 times 2 times 1, so it is just a 6. Okay, so we got dz dt at 0 is 6. Okay, cool. Let's think about more general case. Z is given by a function of x, y, and x is a function of s and t. In the previous one, x is just a function of one variable, but you can see that there are two variables. Sorry. So y is also a function of two variables here. So in this case, you can differentiate z with respect to s and t, and the and the formula are given by like this. But if you are difficult to remember this formula, then you just think about the tree diagram, like a z is a function of x and y, okay? Z is a function of x and y. And you can see that x is a function of s and t. X is a function of s and t. And y is a function of h. No, y is a function of with respect to the variables s and t. Y is also variable x and t. Then you can see that z is a function of s and t. Okay, in the last line, you can see that there are only variables s and t. So g has two variables, two independent variables. So if we think about the, if we think about the derivative, then we need to do a partial derivative, because it has two variables. In the last line, there are two variables. So we want to find the partial derivative with respect to s. In this case, as before, we want to focus on the z and s, okay? Z and s. So in the tree diagram here, let's find the z and s here and find the path joining these ones, z and s. There is one path and there is another path, okay? And as before, just to think about the partial derivative regarding z and x. Z is a function of two variables, so we need to think about the partial derivative. So we use round notation here, dz, and we want a partial derivative, take a partial derivative with respect to x, okay? And here, x is also a function of two variables. So in this case, we do not write like this. We use a partial notation here because there are two variables. Okay. So for this one, we use dz dy, and here it is dy ds. Okay. So dz ds is red one, dz dx times dx ds, okay, plus another root, another path. There is dz dy times dy ds, okay. So this one is the red path and this one is the blue path. So we get the same formula like this. As I said before, since we set z equal to f, it is the same thing, okay? dz dx is same as df dx. Okay, like this, you can find dz dt like this. Joining two lines there, we can get this formula. Okay, let's go to the problem. Okay, here you can see that z is a function. Z is a function for, x and y. And x is a function of s and t. Y is also containing s and t. Okay. So in this case, if we want to find the dz ds, then let's think about the z and s. So here, z and s. So I will write down more quickly. Here is dz dx, and here is dx ds. This is the first one. And the second one, for the second one here is dz dy. And here is for dy ds. So dz ds is same as dz dx times dx ds plus dz dy times dy ds. Okay, cool. Then let me see. To find the dz dx, take a partial derivative here. dz dx. Then we get e to the x sine y. Okay. And to find the dx ds, take a partial derivative with respect to s here. Then we get t squared. Plus, you can get this one from this equation. So you get e to the x cosine y times dy ds is 2st, okay? You get this one, and if you want to represent the equation using only s and t, you can see that using these two equations, you just put here in x and y, so e to the st squared times sine y times t squared plus e to the x times cosine y times 2st. Okay, then you see that dz/ds is the function of s and t. Okay, you can find the dz/dt with the same method I just gave it. Okay, let's go. Okay, it's the same page, but I wanna say more different one. In our setting, we can say that let's say f of x comma y is given by e to the x sine y, and g of x y is given by st squared and s squared t. I think it is not a good notation here. It must be s and t. S and t. And okay. So if we think about this one, then it is like this, and then you can see that g over st is st squared, s squared t. So it means that since our variables of f is x and y, in this case it is x and it is y. Okay, so this setting is the same thing with this setting. Okay, this setting. So in this case, let's think about the differential of, derivative of f composition g. You know, it is the same thing with df times dg, right? And you can calculate it. Here it is it is not a vector valued function. The f is just the, it is fx and fy. It is the same thing with the, gradient f, but it is the f is the matrix notation. So I write like this, and times dg is this is the matrix. Okay, this is the matrix, like if we say it is the first one and it is the second function, then it is a dz d1 ds and dz d1 dt, and this is dz d2 ds and dz d2 dz2 dt, okay? This is the derivative of f. So we get the we get if we differentiate this function with respect to s, then it is t squared, and we get here 2st. 2st is from the, it is, we get this one by calculating ddt st squared, okay? St squared is from the first function. So the second line, we get 2st, st and s squared, okay? So we also can fx and fy, because we know f of x comma y. So let's calculate it, fx and fy. Fx is at e to the x sine y, and fy is e to the x cosine y. Okay. So if we calculate this one, then since it is 1/2 matrix and it is 2/2 matrix, you get 1/2 matrix, right? So it must be 1/2 matrix, and the first entry is given by the calculation like this. I mean e to the x sine y times t squared plus e to the x cosine y times 2st. It is the first entry. It is given by e to the x sine y times t squared plus e to the x cosine y times 2st. Okay, and you want to find the second one. So the second one is given by e to the x sine y times 2st plus e to the x cosine y times s squared. Okay. It was given by these lines. And you can see that this one is the same as we calculated before. Let me see. Here, you can see that dz/ds. We know dz/ds here. I will copy and paste this one. Copy and paste this one. We didn't change x to the s and t, so I will copy and paste this second line. Okay, I will paste here. Okay. This pink line is what we calculated before. It is dz/ds. Okay, and you can see that it is the same thing with this first entry, right? So it means that this first thing, oh my god, this first thing is same as dz/ds, and the second thing is the same as dz/dt. Okay, so you can calculate the dz/ds and dz/dt using the matrix multiplication. I mean, yes, by multiplying these two matrices, you can get dz/ds and dz/dt. Okay, there are two methods. Okay, let's go to the more general case. Here, you have u is a function of x and y and z, okay? And you see that x is the function of r, s, and t. So x is a function of r, s, and t. And y is also a function of r, s, and t. Z is a function of r, s, and t. Okay, so you can see that this function u is u has variables r, s, and t. So there are three types of differentiation: du, ds, or du, dr, or du, dt. Okay. But in this problem, we want to find the du, ds. So we want to focus u and s. There are three s, and there are three paths like this. So you can see that this is du dx, and this line is for dx ds. And this line is du dy, and this line is for dy ds. And this line is for du dz, and this line is for dz ds. Okay, so if we want to find du ds, then chain rule formula is given by du dx times dx ds. This is the first path, okay? Plus, we add the second path, du dy times dy ds, plus the last line, du dz times dz ds. Okay, so by this equation, we can get du dx here. So we get 4 times x cubed y times dx ds. This one is from this one. So if we take a partial derivative, then we get r times e to the t plus du dy. Du dy, here du dy is x to the 4 plus 2y times d cubed times dz dx can be calculated using this equation. So dz ds is r squared sine t. Oh, sorry. I mean, I accidentally calculated, but here must be the du ds, right? dy ds, sorry. Let me check more. du dy was x to the 4 plus 2yz cubed. Okay, so we need to multiply by dy ds. dy ds is 2rs e to the minus t. Okay, plus du dz is given by 3 times y cubed, y squared, z squared, times dz ds is r squared sine t. Okay, cool. Actually, if you want to express this one with respect to the variables only for r, s, and t, then you can use these formula to do that. But you know, we have the specific number here. We want to focus on r equal to 2, s equal to 1, and t equal to 0. So one thing we can do more simpler is just to put these numbers to get x, y, and z. I mean, at this point, at r equal to, s equal to, and t equal to 0, we get x equal to 2 times 1 times e to the 0. It is 2. And y is r times s squared times e to the negative 0. So it must be 2. And z is r squared times s times sine 0. Sine 0 is just 0, so z must be 0. So if we want to calculate du ds if r equal to 2, s equal to 1, t equal to 0, then we just put these things if there is r, t, or s. And since we know that at this point, you know the x, y, z, so we can put this one together. So that we do not need to simplify this one with respect to RST. We just put RST together with X, Y, Z, okay? Because we can calculate the corresponding points with respect to these given RS and T. So let me see, it is 4 times x cubed times y times r times e to the 0 plus x to the 4 plus 2 times y times z times 2 times r times s times e to the 0. Okay. Plus 3 times y squared times z squared. Actually, there is a 0, so it does not matter, but I will write down r squared times sine 0. Okay, then since there is 0, so this term does not affect our result. And the first term gives 4 times, so many 2. Plus 16 plus 4 times 4. Okay, so it has, sorry, here it multiplied by 0, so it must be 0. So the last term is just the 2 to the 4, it is 16 times 4. Okay, in the case, you can see that it is 3 times 16 times 4, so it is the same thing as the 64. So yes, it is 92. Okay, yes, so we calculated it using a chain rule in the general case, in the more general case. Okay, you can generalize the chain rule even if there are more variables, like n variables. You can do that. Okay, let's think about the second derivative. Okay, since you know how to calculate a partial derivative, the second derivative is just the repetition of partial derivative. I mean, here f has a function of 2 variables, x and y, so you can calculate fx and fy, right? So fx is just the f dx, and it is, you can calculate it, 3 times x squared plus 2x times y cubed. Okay, and fy is given by tf dy, and if you calculate it, then you get 3 times x squared y squared minus 4 times y. Okay, so second derivative means take a derivative second times. So you need to differentiate this function again. And you can see that this function is also a function of x and y, right? So we can differentiate this function with respect to x and with respect to y, okay? So we can differentiate the f dx with respect to x and y, respectively. So it is the second derivative, and since we know that the f dx was 3x cubed plus 2xy cubed, we have 6x plus 2y cubed. Okay, and I think we need to be familiar with the notation, another notation like d square f dx squared, like this notation, or this is the partial derivative with respect to x and x. So we use this notation too. So there are many notations, okay? These are all the same things. So in the case, it is d dy, and df dx was 3x squared plus 2xy cubed. And it is the same as the, 6xy squared. Okay. And for this one, we have the notation like d2f dy dx. And it is the f, x first and y. It is a little bit confusing, but you can see that you first differentiate with respect to x here, and then you add y, x and y. Oh, sorry. Since the order is reversed, you need to be careful when you see this notation. Okay. Also fy have two differentiation. It is x and y. So this one was 3x squared y squared minus 4y, so you get 6x here, and this one, oh sorry, here is for the dy. Okay, so this is for the dy, and you get the 3x squared y squared minus 4y, so you have 6x squared y minus 4. Okay. Yes, this is the calculation for the second derivative. Okay, so we calculate the all second derivative here. Actually, second derivative is related to the Hessian matrix. Here, Hessian matrix is the form. Hessian matrix is the form like it is the 2 by 2 matrix here, and it is given by fxx, fxy, fyx, and fyy. So if we want to find the Hessian matrix, the square f or hf, it is just a notation, and this is given by, in this case, fxx is this one, 6x plus 2y cubed, and the fxy is given by 6xy cubed, and the fyx is 6x. I think there is some mistake. Oh yes, you can see that here. If we take a partial derivative, then there must be y cubed, right? The reason why I noticed it here, the mistake of calculation is, by clever rule, I don't know exact the pronunciation of the person, but there is a theorem that fxy is equal to fyx. So we need to figure out that this is the same as this one. So here must be 6xy squared. Okay, and this one is for 6x squared y minus 4. So for this function f, Hessian matrix is given by like this. Okay, cool. Then using Hessian matrix, we can find the local maximum or minimum or saddle point. Okay, first of all, let's think about what the critical point is. If a function f is given and it is a C1 function, that means it's differentiable, then A is a critical point of a function f if gradient f is 0 at point A. Okay. So for C2 function f, for a C2 function, it means that we can differentiate the function f with respect to some point, some direction, second times. So in the case A is a critical point, then by calculating these ones, here actually, um, this means that you know, when you calculate the Hessian matrix, the F11, it is the same as Fxx like that, is positive, and the determinant is positive. Okay, and this one also says that like the you know, I think it's a little bit different with the notation I learned before, but I think I need to figure it out. Yes, it is the same as Fxx is less than 0, and the determinant of a Hessian matrix is positive. Okay, and if the determinant of a Hessian matrix is less than 0, that is, this matrix has positive and negative eigenvalues at the same time, then this critical point is not a local maximum and not a minimum, not a local minimum. And this point is called the saddle point. Okay, it is exactly the saddle point. I mean, you know, there is a holes. I think it does not look like horse. uh, I mean, so yes. So you can see that in this line, this point is the minimum, but you know, for this line, I think it is. I'm not good at drawing, so I'm so sorry for that. But for this line, it is the maximum, so it is not a local maximum or minimum. Okay, I think it is better for you to find a graph or picture for a saddle point in the internet. It is not a good drawing, I think. Sorry about it. Okay, so by using second derivative, in each case, we can say that this point is a local minimum or local maximum, and a saddle point. Okay, we want to apply this theorem in our problem. This is the last problem. Okay, so what I want to do is first find the critical points and determine the critical point is local minimum or local maximum or saddle point. Okay, in this case, first to find the critical point, you know that critical point is the points where gradient f is 0. So we want to find the gradient f first. So gradient f is given by fx and fy. So let's take a partial derivative here. So 4 times x cubed minus 4y, and 4 times y cubed minus 4x. So when the gradient of f is 0, it is, you know, if we take a partial derivative, is it right? Yeah. So we get two conditions. X cubed minus y is equal to 0. Y cubed minus x is equal to 0. So we can see that it is, since this equation, we have y equal to x cubed. So you know, in the second equation, y squared minus x equal to 0, I just put y equal to x cubed here, then we get x to the 9 minus x is 0, and it is x to the a minus 1. So you know that it is x minus 1, x plus, okay. And it is also the same as like this. And you'll see that like this. Since it is 0, we can say that x is 0, or this one be 0. These terms are positive numbers, so it cannot be 0. So there are 3 cases: x is 0, x plus 1 is 0, and x minus 1 is 0. Okay, so we know that there are 3 cases. First one is x equal to 0. The second one is x equal to minus 1. The third one is x equal to 1. Okay, x equal to 0, and x plus 1 equal to 0, and x minus 1 equal to 0. There are 3 cases. We want to apply the second derivative test. So let's think about the Hessian matrix. To say that the Hessian matrix, So it is fxx, fxy, fyx, fyx. Oh, sorry, fyy. Okay. So first thing, we know that fx, and this is fx. So if we take a partial derivative with respect to x, then we get 12 times x cubed here. And if we take a partial derivative with respect to y, then we have minus 4. Okay. And to find the fyx and fyy, we take a derivative, partial derivative here with respect to x and y. So we get minus 4 in 12 times y squared, like this. This is the Hessian matrix. And when x equal to 0, you know, y must be, because we had these regulations, y must be 0, right? Y must be 0. And if x is minus 1, y is also minus 1. And if x is 1, then y is 1. Okay? And you know, in these cases, let's think about the Hessian matrix, just to say HF here. And you know that we just put 0 and 0, x equal to 0 and y equal to 0 here, our Hessian matrix. Then we get 0 minus 4 minus 4 and 0. Okay. In this case, you know that the first one, this one is 0, right? So you can say that if this one is 0, then we cannot verify is a local maximum or minimum or set point, because in its cases we need fxx is bigger than 0, right? And yes, we can verify is determinant is 0 or not. Here determinant is negative, right? Determinant is 0 minus negative 4 times negative 4. It is negative 16. Also, it is negative. So we can say that by the third one, this one, we can say that it's a saddle point. Okay, determinant is negative, so it is a saddle point. So our point is 0, 0, 0, 0 is a saddle point. Okay. Okay, cool. And also you can say that here we have the Hessian matrix 12 minus 4 minus 4 in 12. Okay, so in this case, this one is positive and determinant is it is 12 square. It is 12 square and minus 16. It is positive. Okay, then you can see that the F11 is positive and determinant is positive, then you can see that it is a minimum. Okay, so it is the minimum. At minus 1 comma minus 1, it has a minimum, local minimum. In this case, 1 and 1, x is 1 and y is 1. Then our determinant is, it has the same matrix, right? So determinant is bigger than 0, and our first entry is bigger than 0 positive. So you can say that it is the first case of second derivative. So 1 comma 1 has also in this point, f has a local minimum. Okay. So we found that the x equal to 0, there is one saddle point and there are two local minimum. Okay. Actually, this function, if you draw this graph using a graph calculator or something like that, then you can see that this is like this graph like this. Okay. This point is for the 0, 0. It is saddle point. And there are two local minimum, right? These are minus 1 comma minus 1 and 1 comma 1. Okay, this is the graph of fx comma y. So we can verify local minimum and maximum by our second derivative test. Okay. Okay, I will stop here.